And this is all for the next booklet?
Yeah. Morning, everybody. Welcome to your remote classroom. I see that we're a few more of us in the remote and a few less of us in class, apparently. So good to see you staying home, staying safe. It's a weird thing where I'm talking to like people who can't talk back, right? People in the room are here. Anyways, I do have stuff printed off over here for Equilibrium. We're still trying to figure out what kind of availability there'll be in terms of whether you'll be able to come by and pick things up during the shutdown. It's all still sort of up in the air, so we'll see how it goes. Anybody have any questions about the stuff? Anybody have any questions about stuff before we get started? Yesterday we talked about the heat of a reaction, and we talked about enthalpy, and then we were going to talk about we didn't get to the example questions yet, but we'll get to those today. And so that's what we're going to start today on the example questions. Okay, waiting to see if anybody's got any questions in the chat or in the class. I've got 6 viewers today, wow. So I did figure out that it's not me. I'm not watching myself, so it is a real 6 people. So that's exciting. So that's pretty good, honestly. Okay, so. There are some other options as well. I think this is the best route for us going forward in terms of everybody's able to get on YouTube pretty easily, but there are some options. Yesterday we did a group meeting through Google Hangouts, or what was formerly called Google Hangouts. I think it's Google Hangouts still. And in that way you would also be able to interact because you would all be able to be up on video. And then it'd be like, it's more like a meeting where everybody's equal, sort of a Skype call or a Facebook or a FaceTime kind of thing. So we could go that route as well, but I'm not sure how much anybody would talk or whether they would just use the chat anyways. And then you might as well use YouTube Studio, which everybody has YouTube on their phones already, hopefully. So that's kind of why I'm going with YouTube. Well, let me know if you want to send me a message about some other ideas, maybe stuff you've used in your personal experiences. That would be great stuff too. So I'll just try to get a little bit more screen there. Okay, my least liked part is that all my videos look like I'm on like Mars or something. They're all sort of orangey. But anyways, we were talking about potential energy diagrams. So in this case, with the potential energy diagram, we've got we end up with using an axis like this, where we're going to put our potential energy along the y-axis. And then along the bottom axis is the reaction coordinate. This is a weird axis, honestly. Reaction coordinate. It's sort of, it's very much a, it's not a real variable, right? It's kind of, it's a variable made up to sort of be the description of how far along a chemical reaction is. But then chemical reaction kind of is, it doesn't really happen in a progressive way. In fact, a lot of the time it's sort of a quantum action where the reactants are separate and then they're together. Like they're only in sort of 2 states. The electrons kind of jump between them. So it is a little bit of an odd beast, but that's what we have to use because there isn't really a better solution, at least. You would have thought they would have come up with one in the last, 100 years of chemistry at least. So hydrogen and oxygen, when they react, this is rocket fuel. So in a rocket ship, if you think about the sort of Challenger or whatever, maybe we don't want to think about Challenger, but that's the one below. And So if you've got that rocket, and then it usually is sitting on some giant thing that looks like this, right? And then there's like some side jets on it. This is actually a fuel tank. And inside the fuel tank is liquid hydrogen and liquid oxygen. And then those liquid oxygen, liquid hydrogen are combined, and then those produce the explosive impact that is launching it. And it's exactly 2 to 1, so about 2/3 of it is full of hydrogen gas. You've got sort of 2/3 of hydrogen gas. I don't know why I put my 2 so in a weird spot like that, but this part would be liquid hydrogen gas. Liquid hydrogen, I guess not. And then the other 1/3 would be oxygen. So this would be your O2 and your H2. And so it's just filled full of hydrogen and oxygen, and then they're combined and they cause that sort of explosive power. So, so that means that it's probably exothermic or endothermic. Oh, you're just like, it's so obvious that it's, yeah. Yeah, so hopefully it's obvious that if you've got a bunch of energy being flown out the bottom of the rocket, that's energy that used to be stored in these bonds. So the force that holds this hydrogen and oxygen together is a stronger force than what is required to hold oxygen, or I don't know if I want to say that, but when you reconfigure the hydrogen and oxygens, you release a bunch of energy. So there's a bunch of reasons for this. When we draw oxygen, if we had done a little bit more careful work with like Lewis dots, we would know that there's what's called a double bond here. And double bonds are very strong bonds. They have lots of energy involved in them, but they also have lots of energy. There's lots of energy stored in that bond. And so if you can convert this into 2 single bonds, then you release some of that energy that's used to make that double bond configuration. So that's really the trick. This is a really, I would love to talk about double bonds because it would bring us back to the first unit. We could talk about S and P orbitals again, but we'll leave that for a side conversation another time. Probably never. After the break, maybe, yeah. So down here we have our reactants, and then there'll be some sort of ignition switch, like they might have to, nope, that's an endothermic reaction. What am I doing? Okay, that's better. So this would be the energy to get over this hump would be a small injection of energy, maybe like an ignition switch on your barbecue or something. So that's a little tiny bit of energy pumped in, and then you're going to get this explosive reaction. In the formatting of one of these graphs, there's a couple of options. Sometimes I will put my reaction down here to get it out of the way, and then put the arrow around where the arrow sort of thrown between this hump, and then that sort of indicates that this is where the transition state forms, is somewhere in the middle of the reaction process. It's on this side, it's clearly hydrogen and oxygen, and on this side, it's clearly water. I've also seen people who like to put them right on top. So sometimes we like to do something like this. And then the 2H2O, and that has a nice like visual component to it where you can kind of see like, oh, look, there's a lot more energy stored in H2O, and there's a lot less energy stored in H2. Or in H2 and O2, a lot less energy stored in H2O. So that's another option there. Leave it like this for now. On our graph, we of course are going to have an activation energy barrier. So that is the energy to the transition state. We want to kind of make sure that we are drawing this out nicely. and we're going to label that as EA. And then on the way down, we have this energy difference between the reactants and products. And that is going to be the delta H. Correct. I'm just going to check and see if I can find a calculation for this energy, because I'd like to put it up on the board. I guess we can just. The interesting thing about these, okay, yeah, all right. So, for example, for hydrogen gas, the heat of combustion, which would be this reaction, the reaction with oxygen, is negative 286 kilojoules per mole. So, in this case, delta H is equal to negative 286 kilojoules per mole. So if you can, so one of the reasons we use hydrogen gas or hydrogen liquid in a rocket fuel is actually because, not so much because of the amount of energy. Methane, for example, is 89 kilojoules per mole, but because of the density, you can get a lot more hydrogen into this container than you can methane. So even though methane would burn hotter, the hydrogen is more compact because the molecules are so much smaller. Yeah. Methane is naturally a liquid already, and so it can't be compressed much more. Whereas hydrogen gas can be compressed all the way down to a liquid, making it a very energy dense chemical. So energy density is a really important concept, especially in as we go to renewable fuels. That's one of the biggest concerns, is something like when we burn propane to charge a battery, are we actually going to a higher energy density, or are we lowering our energy density? If you remember your old phones, you used to have like an old Nokia and had that giant battery on the back, and it would only last for, it might last a week, but it wasn't running very high-end software. First iPhone maybe, right? The first iPhones, the big hunking things, and then the battery wouldn't last that long. Energy density was a real important factor there. Now, high density batteries is a really important concept. So, yeah. And so, in this case, not a lot of energy, but it is high density energy. So that's what I was getting. So if you were given this number and then someone said, what's the enthalpy of hydrogen gas? Let's see if I can find something. I can probably just pick a number at this point. So if we then take the potential energy of hydrogen and say the potential energy of our reactants, and let's just give it a number. It's not a real number, but let's say that number is 500 kilojoules per mole. That would depend on the pressure, depends on temperature, a couple of other things. So now this gives us a starting point, right? That says that this is 500, right there. And you can actually now use that to calculate backwards, to use that in combination with this other number we have, the delta H, and you could even determine what is this value down here. So we could take our 500 and take that enthalpy change, which is negative 286, is that what I said?
Mm-hmm.
Okay. And we get 214. So the end products would be 214 kilojoules. if the teacher was nice or mean enough, they could even tell you that, you know, you need to input 40 kilojoules into the system to get the reaction to start. So they say, like, you know, how about if we said, you know, the igniter inputs 40 kilojoules per mole to start the rocket. What would that tell us about what other value are we able to figure out then? That ignition is represented by the activation energy. So now we actually know what the value is of the transition state. We know the transition state is going to be 40 kilojoules more. So it'll be sort of 540 kilojoules for that transition state. So that means we can go up. So I believe that I have a worksheet for that I will try to post ASAP. I gave you the potential energy diagram. You guys got this one yesterday?
Yes.
Yes, okay. So this one's longer. All right, I do have another one about, I just saw today. Postal information rate. The biggest problem is that there are some labs that we need to do, and I'm a little bit worried about how we're going to get to doing labs. I guess I can do the lab and record it in the most boring possible way. Here, this is a handout that I have about representing the reaction with a potential energy diagram and some example questions. So we'll get into this in a bit. These sort of calculations are typically pretty straightforward, honestly. We usually, if I want you to calculate these things, I essentially only have so many options. I can give you the energy of the reactants and the energy of the products and ask you to calculate the delta H. You could get you have 1, 2, 3, 4, 5 different things. So you need to get 3 of them to be able to figure out the other 2. That's really how it kind of works. So let's just go forward to the next one. Now, hydrogen and oxygen do coexist right now. I'm breathing them in as we speak, and they don't explode right now. But one of the reasons they don't explode is partially because the concentration is not very high. They're in the gas form, so the chance of this hydrogen over here, I'm gonna stand over here. This hydrogen here and this oxygen over here actually hitting each other is very low. They're moving quite quickly, shooting all over the place, and they're often passing by each other without hitting each other. The other thing that's missing is this room is not very hot. If we heat the room up hot enough, then we might have that problem where the particles are moving fast enough that they could actually explode, like impact each other and explode. That would be pretty hot though, probably hotter than that'd probably start to boil the water in my body, or I would have other problems before I have to worry about the hydrogen and oxygen exploding in this room. And again, there's just not enough of it to really react. The activation energy is high because there's a need to break the covalent hydrogen-hydrogen bonds in the hydrogen molecules and the oxygen-oxygen bonds in the oxygen molecules. And particularly these ones are very strong. That's why I wish there was a little bit more time to do like proper Lewis dot structures and build some models and things. So get something out of that. Now, there's also one of the things that we can kind of conclude here as well is that because the bonds are hard to break, also implies energy of those bonds could be released. In the case of hydrogen and O2, water has an even stronger form of covalent bond, the polar covalent. How deep I want to go in that hole, but I could talk about that. I could probably talk about that. One example all day, and we would maybe at the end learn something. We're just on page 20 there.
You drink a break if you have a time after making and loading these videos. You always drink 2 videos.
It's true. I just was alerted to a podcast that by a chemist, who by a chemist for everybody else kind of thing. It is called. It's a chemistry podcast from a chemist for other people, and it is called "Chemistry for Your Life" with Melissa and Jam.
Jam?
I guess probably James maybe, but
Okay.
that's what I call my son is Jam.
Yeah, but your son's 3.
Yeah, that's true. Yeah, it's a podcast helping you understand the chemistry of your everyday life. I'll link this on our classroom actually, if anybody's interested. If anybody's a podcast person like myself, it might be something to be interested in. Podcasts are great because you get to listen to them while you walk around, right? So you could be learning while you're on the bus, which nobody's taking the bus anymore, but you know,
Past like 3 buses, they were all empty.
imagine now.
Yeah, I've started walking to work after school because the bus is so overcrowded when I take it to work.
Oh, is it still overcrowded?
Well, it usually is, so I don't want to like.
I feel like it's pretty funny though. It's like all the buses are empty. Why not take one of them? Like,
Right.
Like if they're empty.
I just found out though that they don't clean buses very often.
I'm sure they must have changed that policy since.
Well, now because
Yeah.
of the thing, but like it came out that they only clean
Huh.
them like every
Not let me link it.
4 or 6 months or something.
Oh shit. That'd be always like at least
On the outside. Truly disgusting. But I carry hand sanitizer and wet wipes with me all the time, so
It's not like my link. Okay, well, I'll figure that out later.
Are these meant to be?
They are up already. They should be. Are they not?
No, it's just
Okay, good. Yeah, they should be up there already. Yeah. I mean, yeah, there's lots to be talked about in terms of double bonds versus triple bonds and things like that. How much energy is stored in them. Okay, so let's talk about this other chemical reaction. So this is a. Think about this. It looks like it's. I'm going to assume they meant this to be an endothermic reaction, but I have to think about it. Maybe. Okay. Having taught organic chemistry, this bothers me that this reaction's in here because it looks like it probably is exothermic. We're going to assume it's endothermic. The good thing about organic chemistry is you can just change the solvent and that will make it endothermic. So, assuming this is an endothermic reaction, we're again going to put our potential energy up here. One of the things I'll be looking for in terms of drawing out one of these graphs is for you to be able to properly label the axes. Reaction coordinate. And we'll put a bar down here somewhere. And then we're going to put a little up and a down. I think ethylbromine. And so then we're going to put our reactants. And as I was saying in the previous example, we can either write the chemical reaction on the bottom, or sometimes you'll see this sort of written here. I'm going to try both. So see, I get to this point and then I go, oh no, I ran out of space. So it is a little bit of you have to sort of plan ahead a little bit and make sure you have space, or you have a device that can let you fix your mistakes here. Printer somewhere's going on. Okay, and so those would be the two reactants. So the idea here is that if you were to expose ethyl bromide to some hydroxide, so to a strong base, then you would get a displacement of the strong base of the bromine with a hydroxide. But to do that reaction, you would essentially need to heat the system up. You would need to put energy into the system because this state of molecule is much more stable than this state. So we are starting at a position of low potential energy, and we're going to a position of high potential energy, or a state of high potential energy. So this means that there must have been energy put into the system. The enthalpy describes the energy inside of a system. If the energy has increased, then that means the energy must have come from somewhere. And in this case, it would be coming from the universe. So this would be an endothermic reaction, yeah. And so what we have here is we have a beaker like this, where your reactants are inside the beaker, and then energy, photons, have to be entering this beaker, and they have to be entering the beaker to change the state to a new state. The universe is donating energy to your system. So what does this beaker feel like to touch it? Okay, it could be warm. The beaker is stealing energy. What would it feel like if something stole energy from you? What happens when you step outside right now? Enter outside. Does energy get stolen from you when you step outside? feel cold, right? Yeah. So the energy that's in your hand goes to the air around you. And you start to get this, you have like a little tiny layer of hotter air around you as your body heats the air around you. And then that air like disperses. So when something is stealing energy, when something is undergoing an endothermic process, it will feel cold because it is absorbing energy from any source it can. If we put a thermometer in the jar, the thermometer will donate its energy to the endothermic reaction. It'll try to help the endothermic reaction along, and the thermometer will lose energy, and that will cause the thermometer to go down. So the universe has less kinetic energy at the end of this reaction.
Can you tell from the equation what kind of reaction we'll be expecting?
I can, but I don't think anybody else can. No, so I mean, from organic chemistry, you could figure it out that if you in like a second year organic course, you would study these reactions and like learn which ones are spontaneous and which ones aren't. This one, I'm still surprised. I feel like this reaction does happen this way, but I might be wrong. So I feel like this is actually a spontaneous reaction, but that's only my intuition, not.
So we won't be tested on that.
No, you never have to guess. Sometimes in the previous example, we did rocket fuel, and it's like, well, rocket fuel, we know the results are rockets, right? So probably an endothermic reaction. If we did the chemical reaction in the class, we could also tell by looking at the results. So some things to think about in terms of the way the chemicals are arranged, and what we're going to talk about in the next section is to think about what kind of chemical bonds do we have now, and which kind of chemical bonds do we have later. Yeah, see, this is why to me this is a really convincing argument that it should be exothermic. But anyways, I'm going to assume that they did something special. Sometimes you can make an endothermic reaction. Or an exothermic reaction endothermic by changing the conditions as well. So in this case, we have an increase in potential energy. And so we want to draw out the last couple of details here. We want to draw out the activation energy. So this is going to be the activation energy. And we're also going to draw out the delta H. Notice that in this case, delta H is positive. It's actually probably better just to write it that way. And so this is greater than 0. So this is an endothermic reaction. I'm going to just write a little bit down here about that idea of where the energy comes from. The endothermic reaction proceeds by taking kinetic energy from the surrounding converting it to potential chemicals. Wow, I'm writing more than I expected to write there, but probably too wordy. So the idea here is that an endothermic reaction proceeds by taking kinetic energy from its surroundings or from its universe and sucking that energy into the system and reaching a new state. This new state has a higher potential energy than its initial state, so that means there's less kinetic energy in the universe, less kinetic energy in the surroundings. These chemical reactions feel cold. If you want them to keep reacting, you're going to have to keep providing them energy. What are some examples you can think of in your day-to-day life where you have to continually provide energy to the system before the product is formed? A couple easy ones out there. How about cooking? Was there any examples where you have to kind of keep pumping energy into it to get the reaction to form a new form? Maybe baking a cake. I'm thinking about baking a cake. I'm thinking about that. Is that an endothermic reaction? I think so. I think you need to provide energy throughout the cake baking process. You don't just provide energy at the beginning and then take it out and put it on the counter and let the reaction keep going. If you let the action cool, it stops working, right? And you will get a terrible tasting cake. So if you take the cake out too early, right, there's still sliminess in the inside. You're going from a liquid state to a solid state. So that usually implies that the atoms have been rearranged in a way that's more complicated. And liquids are they're simpler. The liquids, the particles are just in a random organization. If you make that solid cake shape, all of those atoms have to be in very specific places and very specific sort of orientations to make those different starchy molecules and to make those, sugar molecules and stuff that are supporting the cake. So that seems like a situation where you're putting energy in to get to a higher potential state. There are a couple things that are happening that are probably exothermic, like carbon dioxide coming off and like the bubbles that form in your cake. But I think overall you have an endothermic reaction. So here we have some calculation questions. So I'm going to give you a few minutes to work on these. This is a very similar sort of idea to what we saw previously, and I'll also come around and hand out another worksheet on this. It looks like this. I'll try to get that to you in the materials section if you're online right now. This. So if you can do the ones in the booklet, then we'll do those together as a class right away. Here's some additional practice. We'll also come around with a stapler so you can see the two. Great. If you are in terms of posterity or being protective, this is all stuff for the kinetics unit, for the not kinetics unit, but the equilibrium unit. So if you want to grab one of each of these, that would be great to take home today, just in case the school suddenly gets shut down or whatever. It's Wednesday right now. I have them in booklet form, and I also have them with the hole punches. If anybody wants hole punch versus booklet. Same, yeah. Some people like a binder, but this one's booklet. Maybe when it's a break, Nick, I'll do like do the lecture part really only takes half an hour, so when I do like half an hour lecture, and they say like, okay, this is where you guys should be starting work on activities, then I'll record a separate video, maybe on something.
Oh, I was just suggesting that was fun.
Yeah, no, it's a good idea. I like fun.
I like fun.
This is some chemical, we're almost close to the end of the chemical kinetics test. I have no idea how I'm gonna do like, I think this is a good reason to get rid of tests right here, is that we probably aren't gonna be able to do them for the next 3 weeks. So we will probably do some, they'll have to be like online assignments of some sort. This one for hand-in. Well, everything's for hand-in. Anything can be evidence that you know how to do it. So I'll post it right now. Yes. I'll post in a second.
Which one is the test reactions in this one?
To reverse it. To reverse it, you would move backwards along the graph.
So it's gonna be this,
So it would be this forming path. That would be the reverse.
this will be the test.
That would be reverse reaction. This would be the product of the reverse reaction. Is that what you're asking?
Do the statement.
I do have a stapler, yes. I'm going to get that for you. Then our friends at home just need some supplies here, so I'm gonna get on here and post some things for them. I'm gonna just put them in the kinetics section. Also, this afternoon, I'll try to post up all of the stuff you need for the equilibrium unit, so you can start working on that and work ahead if you like, or not. This, and I also just handed out this. Potential energy diagram. All right, if you are online, you should see on your Google Classroom that I just posted the assignments that everybody's working on in class right now. Although we will work on these practice ones right away so that you can find those assignments quite trivial, I'm assuming. So we'll just we'll take a minute. Although there's not much of a minute left, is there?
So think about is the potential energy laser beams
So potential energy increase, kinetic energy decrease. And what was it? Potential energy, if your system's energy is increasing, then the universe's energy is decreasing. So it's endo, the energy is going in. If your system's energy is decreasing, then the universe is increasing. So that's exo. Energy is going out to the universe. Okay, so let's just give us a look as we have only a few minutes left. So, I have the advantage of having built-in rulers here. So I'm just gonna grab mine and move that here. So not a perfect graphic at all, but this is essentially what you want to do on one of these questions is just kind of draw a line through the major points of the graph, of the curve. What do we call it? Minimums and the maximums, I guess. If this was a, if this was a parabola. And so looking at this graph, what is the activation energy of the reactants shown on this diagram? The activation energy will be from your lowest point or from your reaction point up to the highest point. So the activation energy is equal to the heat of reactants. And, what do we want to say? We want to say, let's just use energy maybe. Energy of the transition state minus the energy of the reactants. And so I don't know what we're gonna call this. This is gonna be 95 maybe. Let's call this 95 and 35, just to make it easy. So 95 minus 35. Oh, not 35, 20 reactants. So we got E react, E product, E transition state. And so we get 75, probably like kilojoules or something. No units are given, so we can't really make units up, I guess. What is the enthalpy change in the reaction? So that's going to be our change in H, which is equal to the difference between the products minus the reactants. This is one where you do have to do it in that order. You can't flip them around. You have to do products minus reactants. And so if that's the case, then I'm going to take this 35 and I'm going to subtract the 20 and notice that I get a positive value, positive 15. So that tells me that it's a positive value, so positive delta H. This implies an endothermic reaction. So I'm going to ask this next question, what is the activated complex or transition state? We can say this is sort of a high energy, one definition I like is sort of like a high energy arrangement of the reacting molecules where they can form either the products or the reactants. They can equally form either the reactants or the products, something like that. Usually I like to see the idea that from the transition state, it's exactly the tip over point. And it's sometimes they're gonna form this way, sometimes they're gonna fall back apart. Once they hit that sort of transition, it's the exact point in between. If they fall apart, then you get a whole bunch of energy out, or maybe you don't. And if they don't, but it's the tipping point. So it's a high energy arrangement of the reacting atoms that can equally form the product or reform the reactants. And it's the only point where that's true. Anything else? So if you step one step closer to the other side of the transition state, then those molecules will much more likely form the product than the reactant. It's not equal anymore. If you form one more onto the other side, if you're one step to the other direction, it's the only point where the atoms are exactly at the right position that they can equally form the reactant or the product. Hence the term transition. What do they call it? What is it in pre-cal? It's like that point on the top of a curve,
Vertex.
Yeah, vertex. Yeah. If on this curve here, this point here, right? It's the only point where the slope is flat. It's at any point to the right or left, the tangent is going to be angled in either the positive or negative. Even if it's like 0.00001, it's still positive 0.001 or negative 0.00001. So anything to the transition point is exactly that. It's a point on a curve. And so it should be the exact point where neither is more likely or less likely. Okay, we better wrap up here as we get to our next class, but please do the last question. I will try to put in the answer key later today, and and then tomorrow we'll talk about factors affecting rate. This is probably my least favorite lesson because it's the most hand wavy, even though I love hand wavy stuff. You don't really have I feel like you were lacking a lot of background, so we'll see how long I stick into this lesson before I just abandon it. That's what happened last time, because I got about halfway through and I said, this lesson makes no sense. So we'll see. It's on my chopping block for reorganizing this unit. But after that, we have lesson 5, which I believe is reaction mechanisms, which is really cool. I love this one for making you think outside the box and propose some fun ideas about how things could happen. And again, it's probably a little bit outside of our comfort zone. And then we have the rate law, which is actually the most important part, probably for the rest of this course. So this unit is this unit in that lesson 6 It forms the fundamental building block that is part of the next 3 units. And so all 3 units land on this initial idea that we get out of lesson 6. All of the rest of the units are built on that, and until we get to electrochemistry at the very end, and that's like a completely different subject. That one connects mostly to the first unit. So we're on the precipice of what becomes the big fan for the rest of the course. So everything else builds out from this one lesson, and then we come back with like a random lesson at the end, or a random unit on electrochemistry. Probably my favorite unit. Anyways, thanks everybody. Have a great day. Thanks for showing up on the stream. It was good to see you. We'll talk to you later.